So my name is Jeff Hittinger. I'm an alumni of the program. It's my honor to chair the House Award Committee and to introduce the House Award winner this year. The House Award was made in remembrance of Frederick Anthony Howes. He was the program manager at the Department of Energy Applied Mathematical Sciences program back when this fellowship was actually founded. He was a strong advocate for the program, also a fierce advocate for computational science in general. And at that time, it was in the 90s, it was really just an emerging field. Dr. Howes was also a very committed public servant and person of high integrity. And frankly, all of us in our computational science community have benefited from his passion and vision. I have the honor, or in his honor, we select each year an alumni as the House Scholar from the graduating class, so the fellows who have graduated the year before. The criteria for that are fellows who have demonstrated exceptional leadership, outstanding character, and also exceptional technical achievement. So I'm pleased this year to announce that the House Scholar Award winner is Dr. Eric Isaacs. And I will read here the citation, and then we'll invite him up here to give a talk about his work. So the House Scholar Selection Committee is pleased to name Dr. Eric Isaacs as the 2017 House Scholar in Computational Science. Dr. Isaacs earned his PhD in Applied Physics from Columbia University in 2016. He is now a postdoctoral research associate in the Department of Materials Science and Engineering at Northwestern University. Eric's selection as the 2017 House Scholars reflects both his outstanding scientific achievements and his demonstrated leadership and character. Eric's research has already pushed the forefront of many areas in computational materials physics. Specifically, he performed the first ever combined density functional theory and dynamical mean field theory calculations of the voltage and phase stability of lithium-ion battery cathode materials, which required massive quantum Monte Carlo calculations. Eric provided new understanding of the physics of low-dimensional materials, such as the mechanical failure of two-dimensional materials, and of strong electronic correlations in layered transitional metal. All right, you told me how to pronounce this, and I'm not going to get it right. Dichol cogenides. Close? All right. Similar to graphene. Finally, in collaboration with scientists at Brookhaven and Lawrence Berkeley National Laboratories, he demonstrated the significant role of interface morphology on the properties of photocatalytic and photovoltaic cells. In his postdoctoral work, he is exploring materials informatics and using materials data sets combined with data mining and machine learning techniques to accelerate search for novel materials. In addition to his strong aptitude for research, Eric has a long history of leadership and community service, with a strong commitment toward education and outreach to underprivileged communities. As an undergraduate, he traveled to New Orleans to help with the rebuilding efforts after Hurricane Katrina and Rita, and while there, also tutored underprivileged middle school children in math and science. As a graduate student, he participated in the joint U.S.-Africa Materials Initiative, spending a week in Ethiopia interacting with Ethiopian students and faculty from local universities. From that experience, he initiated a collaboration with a Tanzanian researcher from the University of Dar es Salaam on the electrosynthesis of organic compounds from locally available resources. More recently, he volunteered in Northwestern's mentorship opportunities for research engagement, introducing high school students to the basic principles of material science and more generally the fundamentals of thinking like a researcher. Eric's demonstrated excellence in research, leadership, and outreach exemplifies the qualities Fred Howes encouraged in all young scientists. He serves as a role model to both his peers and future generations of scientists, and he's a committed advocate for the field of computational science. Please help me in congratulating Eric. Wow, the box got big. I don't know what's in here. It used to be a much smaller box. So as part of the award, he gets a check and this nice gift from Tiffany's.
Thank you very much.
So how are we going to pose for this thing? All right. And part of his award is that he has to now give you a talk right after lunch and keep you all awake. So I'm not sure that's a prize. Go ahead.
All right. Well, thank you very much for the most kind introduction. I'm happy to be here today to discuss some of my research and just in general to be back at this nice conference. And so today I'd like to discuss some of my research in which we use high-performance computing in combination with quantum simulations in order to design and discover materials with very particular electronic properties. Now, before I get into all of that, I'd like to thank and acknowledge a few people. First of all, Fred Howes, and as well as his family, the DOE CSGF program, and the Krell Institute for creating such a nice community and a great program. I also, at this time, want to remember Jim Coronas, who just recently passed away, as was mentioned, and was another stalwart of this program. Finally, I want to thank my nominators, the House Committee, as well as my academic advisors. So today, first, I want to give you a brief introduction into the quantum simulation of materials. In particular, how can we simulate and understand materials in which the electrons interact especially strongly, or they are so-called strongly correlated electrons. And then I want to discuss what is this special property of a single band correlated material, and why is that so special, why is that so rare? And then I'll discuss two different approaches in which we try to design such a material. The first, I'll focus on one particular material, vanadium disulfide. And in the second component, I'll take a broader, more systematic approach using materials informatics in order to try to systematically screen for such compounds. So if we want to understand some n-electron system, say a molecule or a solid, in quantum mechanics, in principle, we should solve the famous Schrodinger equation for the wave function psi and the total energy E. Now, you can see from how I've written this equation that the fundamental object here, that wave function psi, is a function of the positions of each of the n electrons, so R1 through Rn. So therefore, this is a 3n dimensional problem. So to solve this problem, the solution to this problem scales at best exponentially with n, so this is a very poor scaling. To give you some idea of that, if you suppose I can solve just a one electron problem on 1 second on my computer, as I go to 2, 10, 20, 100 electrons, the time to solution would be at least 3 seconds to several hours, to several years, and then you get to 10 to the 35th years, this really astronomical amount of time. So I'd really like to not wait so long for the answer, and that's the reason this is such a significant problem, this exponential scaling. This is the so-called many-body problem in electronic structure. Don't worry, there are a few approaches in which we can get around this scaling. Generally speaking, the first comes from the chemistry community, in which one still works with the wave function, but one builds it up from some truncated number of sets of single particle wave functions or orbitals. There is, however, an alternative approach originating from the physics community, in which we say, let's actually forget about this wave function, this massive object. It really contains more information than we actually care about. And instead to work with another much simpler function called the electron density, or ρ. So this is now just a 3-dimensional function, and it just tells us about the overall distribution of all the n electrons in space. This latter approach is called density functional theory, or DFT, and there are two essential components. The first came from Hohenberg and Kohn, who proved that energy, E, is a unique functional of this electron density, which is minimized for the lowest energy, or the ground state. So all that means is, in principle, if I restrict my interest to the ground state, yes, I can circumvent dealing with this complicated wave function, and instead I can work with this much simpler density. Now, the second component came from Kohn and Sham. They had this idea of actually constructing that exact electron density from an auxiliary system of non-interacting electrons sitting in some weird effective potential, which we now call the Kohn-Sham potential. So the basic idea here is we take our many-body problem, in which we have all the Coulomb interactions between all the different electrons, and we map it onto this now non-interacting problem. So we deal with a single electron at a time, and it's sitting in this effective potential. That Kohn-Sham potential is designed to mimic the effect of the other electrons. So we mapped down from a 3n-dimensional problem to a 3-dimensional problem, so this is a pretty dramatic simplification. The remarkable thing is everything I've told you so far is exact. I've made no approximation. So what is the catch here? The catch is that while we know this cone-sham potential exists, in practice we don't know what it is. So in practical density functional theory, we have to approximate the cone-sham potential. Typically, this is done using the exact results, but for a model system. So we haven't introduced any empiricism, any experimental input, but we do have approximations in practice in this theory. That said, this density functional theory has been enormously successful across the periodic table. It's essentially become our kind of standard model in material science. So there is a class of systems for which DFT can fail, in the sense that our common approximations to this cone-sham potential don't accurately describe the physics. This is what we mean when we talk about strongly correlated materials. So these are systems usually when one has a partially filled d or f electron shell, so kind of further down in the periodic table. Those orbitals are much more spatially localized, and because of that, the Coulomb interaction is especially large, and in practice, the cone-sham potential can fail to describe these materials. So what can we do in these situations in which we have strong electronic correlations? One approach is as follows. You can imagine picking out some subset of the electronic degrees of freedom, namely those localized d or f orbitals. So for example, here's a d orbital on a transition metal site in a crystal. One can include an explicit Coulomb interaction, which we call U, just within this subspace, and then we can just use DFT for the remaining degrees of freedom. In what's called the dynamical mean field theory approach, now it's DMFT, the idea is to perform another kind of mapping. So you have your intractable many-body problem on a lattice. You can imagine plucking out one of those lattice sites, treating the Coulomb interaction exactly on that site, and then coupling this site to an auxiliary electron bath or reservoir to which and from which electrons can hop. And the key here is that this electron bath's parameters are chosen self-consistently to mimic the effect of those discarded lattice sites now. So what we do in dynamical mean field theory is we map our many-body problem onto this problem of kind of one lattice site coupled to a bath. This is what's called a quantum impurity problem. And so the quantum impurity problem is still a many-body problem, but it's just a much, much simpler one than the full problem. And so in dynamical mean field theory, because electrons can hop on and off this site, we capture the electron dynamics of those interactions, of those correlations. It is a local approximation since we only explicitly have one site. If we solve this quantum impurity problem exactly using, for example, quantum Monte Carlo calculations, then we have what's called DFT plus DMFT. So there we're numerically exactly solving this problem. So in my fourth year talk, I discussed these very computationally intensive DFT plus DMFT calculations on battery cathode materials. There is, however, more computationally inexpensive strategies to solve this quantum impurity problem. One is called DFT plus U, in which we basically just take an approximate solution. It's a mean field solution to this quantum impurity problem. So this is a significant approximation, but it's so much computationally cheaper and still gives us a lot of insight into the correlation physics in these materials. And therefore, in this talk, I'm going to focus mainly on results, not entirely, but from density functional theory as well as the density functional theory plus U, this approximate solution to the quantum impurity problem. So probably the most well-known class of these strongly correlated materials are called the cuprates. So these are very famous copper oxide ceramic materials. They were shown back in the 80s to exhibit this remarkable property of unconventional high-temperature superconductivity. So electricity can flow with zero resistance. In addition, these show interesting levitation properties, as shown here, since they completely expel magnetic fields. And although these materials were discovered in the late 80s, the details of the mechanism of the superconductivity are actually still debated today and not fully settled. That's largely because it turns out that these cuprates just have a very, very complicated phase diagram. This is still an active area of research. But one very important aspect of these cuprates that's crucial to the high temperature of the superconductivity is the fact that you have a single orbital, a single d orbital that's relevant to the physics. So the other correlated, the other d orbitals are separated in energy. So this is a very rare property of the cuprates. It's basically the only material with this property. The minimal model for this physics is called the one-band Hubbard model. So it's one band just because we have that 1d orbital. And the Hubbard model is this famous model Hamiltonian. I can describe it pictorially here. There are basically two terms. One's called a hopping term. So this is just a lattice, and electrons can hop from site to site, and that's favorable with energy minus T. But if I have two electrons on the same site, they're going to repel each other electrostatically, and you pay a Coulomb repulsion cost of plus U. So basically, this hopping term leads to delocalized electrons and metallic behavior. But if we crank up U enough, actually this tends to localize the electrons, and one gets insulating behavior. And so if we have a large U compared to T, then we're in a more correlated regime, and one can actually get a correlation-induced insulating behavior. So this is a special kind of insulator called a Mott insulator. So the cuprates are described by this physics. And although this model is extremely easy to write down, you can see this is a many-body Hamiltonian, and in general cannot be solved other than special cases of one and infinite dimensional case. And so what we'd like to do is to be able to discover some other correlated one-band material. We only have the cuprates now, and the phase diagram is very complicated. So it would be great if we could find more materials that are similar to the cuprates. One, because, hey, we might discover some high-temperature superconductor or some other interesting strong correlation physics phenomena. And secondly, because it would be great to have another system with which we could benchmark all of our many theories of strong correlation physics. So there's kind of two goals, two reasons behind this goal here. So why is that so complicated? It sounds simple, just one band. And the reason is basically, in most transition metal compounds, you really just have too much local symmetry. So the coordination of most transition metal compounds is either octahedral or tetrahedral. And just from group theory, from symmetry, that splits the 5d orbitals into a group of 3, which we call T, and a group of 2 called E, for both of these cases. So essentially, because you have this high symmetry and you have this high degeneracy of these d orbitals, we've realized many multi-band Hubbard models in practice in many transition metal compounds, but a one-band model is really exceptionally rare. There have been, decades-long searches for new superconductors, especially ones similar to the cuprates. Unfortunately, that haven't been successful. I'll mention a few recent strategies or ideas to try to achieve this one-band model. So the first was to take an octahedral compound, namely lanthanum nickelate, and to form a kind of complex structure in which one makes a superlattice, so one layer of lanthanum nickelate and one layer of lanthanum aluminate, and then to go sort of every other. And the idea here was simply to just explicitly break the symmetry of those two e orbitals. So you get one that goes up in energy, one that goes down, and hopefully you get this kind of one-band correlated material. Unfortunately, the experiments have shown that really one just doesn't get enough symmetry breaking. So it seems like starting from a high symmetry coordination like octahedral is difficult to achieve a one-band model. A second theoretical proposal was to look at this distinct coordination called Trigonal Bipyramidal, which now is low enough symmetry that one in principle can achieve a one-band kind of model. Unfortunately, it was shown that these compounds are actually not thermodynamically stable. So it seems, even though they could be interesting, it's unclear if these could actually be synthesized. So what I'm going to do is in my approaches, I'm going to take two things into consideration based on this. First of all, I'm going to avoid any high symmetry configurations. So I'm going to ignore anything that's, for example, octahedral or tetrahedral, because it seems like it's just too hard to break the symmetry from that high symmetry starting point. And secondly, I'm going to explicitly consider thermodynamics. So we have a high probability of actually being able to make anything that we discover. So in this next part, I'm going to focus on this specific material, vanadium disulfide, in a particular coordination called Trigonal Prismatic. So these kind of materials, in general, have two possible structures. So these are layered compounds. So I'm just looking at a single layer here. And you can see on the top we have an octahedral coordination. So that's not what I'm interested in because it's higher symmetry. But there's also a distinct coordination called Trigonal Prismatic. Basically, you just have your metal coordinated by this triangular prism. And the nice thing about this is that from the group theory, we now split the d orbitals into a group of two, and then a group of one. Just this one singly degenerate orbital. So that's exactly what I'm looking for. So I would like to just fill up this orbital halfway just with one electron. Now, we choose vanadium disulfide not only because it'll have, in principle, that isolated level from group theory, but also vanadium would nominally be in a D1 configuration. So that's exactly what I'm looking for. In addition, by choosing vanadium, those are 3D orbitals. Those tend to be the most localized, so the most susceptible to this strong correlation physics. So this could open up, in principle, the possibility of this rare one-band correlated material in analogy to the cuprates. Now, it turns out that vanadium disulfide does already exist in this octahedral form, but this new trigonal prismatic polymorph is what we're interested in here. So we can apply our quantum simulations and see, does this simple kind of cartoon picture actually work? So here I can plot just within density functional theory the dispersion relation, what's called the band structure for this material. Basically, everything below zero corresponds to occupied electrons, above are unoccupied. And you can see here that indeed we do have this one half-filled isolated level. So that's exactly what we were looking for. You can see there's a gap between it and the sulfur p states below. You can see that there's a gap between it and the other vanadium d states above. If you integrate over all of the wave vectors, you get the overall electronic spectrum, which just indicates that this is a d orbital, and in particular, it's this dz squared orbital. So you have one kind of lobe, and then you have a donut going around it. And so we are able, with trigonal prismatic VS2, to achieve this one-band correlated material, this rare property of the cuprates. So we wanted to understand this a little better to see how we were able to achieve this rare electronic structure. Now, one of the nice things about theory and computation is that we can actually, at the microscopic level, really gain an understanding of the physics of these things. And so we can basically turn on and off different orbital interactions, for example, between the vanadium orbitals and the sulfur and the vanadium-vanadium interaction. And you can see here this is just that spectrum turned sideways, that here with the vanadium-vanadium and vanadium-sulfur interaction, we're qualitatively reproducing this feature. We have this single isolated band. However, we find that if I remove that nearest neighbor vanadium-vanadium interaction, so this kind of electron hopping, that actually we would get a qualitatively different spectra, and we would lose that one band quality. So we would still have the gap below, but we would miss that gap above. So what does this mean? This essentially tells us that it wasn't just that trigonal prismatic coordination that allowed us to achieve this rare property, but also appreciable vanadium-vanadium direct interaction, direct electron hopping that allows this single-band correlated electronic structure. So now that we've achieved that property, we wanted to see, okay, can we actually make this thing? So we wanted to consider the thermodynamics. So basically, we computed the energy of different structural, electronic, and magnetic states to see what's lowest in energy and by how much. And so if you first look on the right here, you'll see we have to consider our existing octahedral phase to see if it's higher or lower in energy. You can see we have a non-magnetic configuration. There's a magnetic instability that lowers the energy. Experimentally, it's known that there's this complicated structural distortion called a charge density wave in this system. We capture that further lowers the energy. But the important thing here is that if you look to the left on the trigonal prismatic side, you can see that the lowest energy state is actually trigonal prismatic. So this is the phase that doesn't yet exist, but we actually find that it's significantly lower in energy than the octahedral. So already this is promising that this thing should be able to exist. We find it's thermodynamically stable. Furthermore, so this trigonal prismatic compound, you can see within DFT has a strong magnetic instability. So we find what's called a ferromagnetic ground state. And the magnetism in this system is so strong that even within DFT, already it fully spin polarizes. So we already have an insulator even at the level of band theory. So that's a strong indication that we have signatures of strong electronic correlation. Now we can explicitly explore the role of electronic correlation by going beyond density functional theory using that DFT plus U approach in which we solve our DMFT equations with an approximate solution. So this is the electronic spectrum of that magnetic state. You can see basically our isolated band is just spin split. So this is just within DFT, or U equals 0 essentially. If one then adds on that explicit Coulomb interaction, you can see the main effect is just, this works, that it makes it increasingly insulating. And the interesting thing here is that, I'm not showing you, but we look at many other different magnetic configurations. So here all the spins are aligned, but we can look at ones that are anti-aligned in various configurations. And actually all of those are insulating. So what that tells us is that we are in that special kind of phase called a Mott insulator, in which it's not just some particular magnetism that's leading to the insulating behavior, but it's actually the electronic correlations themselves. So that's very interesting to find. We can also assess how the thermodynamics are affected by the strong electronic correlations. So here I plot the total energy of trigonal prismatic compared to octahedral. So within DFT, it's negative because it was stable. And we note that as we increase U, as we move to the right, initially the stability is actually increased, so it's further stabilized. Though for sufficiently high U within DFT plus U, this trigonal prismatic phase does become destabilized. However, using the more accurate DFT plus DMFT calculations, that is, solving that quantum impurity problem exactly, we find that trigonal prismatic VS2 remains the ground state. So this is pretty convincing evidence that not only would this be a one-band model, not only would it be show signatures of strong electronic correlations, but actually there's a very good shot that this thing should be able to exist. So in this trigonal prismatic VS2, we've achieved this rare one-band electronic structure analogous to the cuprates. We have significant evidence for the thermodynamic as well as the dynamic stability. And this, if synthesized, could really enable unprecedented studies of strong correlation physics and Mott insulating behavior. So we're very excited about this material. You can see here that we really came up with one particular material via some simple rules, kind of staring at the periodic table for a while, and we studied it in depth. Another thing we wanted to do is to see if we could more systematically look for additional compounds. In particular, we wanted to see, can this emerging area of materials informatics accelerate this search? Can we find more things that, like trigonal prismatic VS2, seem to have this kind of desired electronic structure? So what I've done is I've used what's called the Open Quantum Materials Database, or OQMD. This is developed at my institution at Northwestern University, and it is a database using density functional theory as well as DFT plus U, so the same level of theory, of over 500,000 known and hypothetical materials. So the idea here is we take experimental crystal structures as well as crystallographic prototypes On our local clusters, as well as supercomputers, we run many, many electronic structure calculations at a consistent parameter set such that we can do interesting thermodynamic analyses and generate this nice kind of queryable database. And we use this to try to answer different questions in material science. So we devised a kind of screening strategy to look for this special electronic property of this single band correlated material based on a few factors. So first of all, we consider chemistry. So we're going to want something with a transition metal coordinated to some anion. We're also, to be practical, going to ignore anything with radioactive elements. That's not so interesting to us. Secondly, we're going to look at the local structure, so that coordination environment of the transition metal. So we want some suitable coordination such that the symmetry is broken enough that, in principle, we can have one isolated d orbital. So, for example, there are several of those, but one of them is just that Trigonal Prismatic we just talked about. And so there you just want 6 nearest neighbors and these particular bond angles corresponding to that kind of shape. For each of these suitable coordination, we also want to consider the nominal d electron count on the transition metal such that we can achieve this half-filled isolated level from crystal field theory. So for example, for that Trigonal Prismatic phase, based on that splitting, we just wanted a d1 system, or 1 d electron on that transition metal. And finally, we consider explicitly the thermodynamics. So in thermodynamics, the stable compounds are the ones whose formation energy as a function of composition sits on this geometric construction called a convex hull. It just means there's no other linear combination of phases that can lower the energy. So we consider any compound that's on the convex hull. We also, if it's pretty close to the convex hull, we call it metastable. And additionally, to be practical, if there's something that's not too close to the convex hull, but it's been reported experimentally, we're still going to consider that because someone's made it before. So when we implement this strategy, what do we find? In terms of absolute numbers, here I plot the number of compounds we find. This is on a log scale, or you wouldn't be able to see it as I screen, going from left to right. So we start out with all of our known materials, this kind of so-called haystack. So this is 550,000 total materials we have in our database currently. We lose about 100,000 when we screen in terms of removing anything that's radioactive. When we consider the thermodynamics, the stability, now we lose about an order of magnitude. We're down to 43,000. When we screen by chemistry, we're down to 18,000. D electron count, then we only have 4,000. And finally, when we consider the structure, now we only have 187 candidate compounds. You can see in various local coordinations. If we break this down in terms of the different structures, you can see that square planar coordination really dominates about half of the compounds we find. A good amount of linear as well as trigonal prismatic compounds. In addition, in terms of stability, you can see that a little under half are stable, about a third are almost stable, we say metastable, and then a little less than a quarter are those that are predicted to be unstable, but they've been experimentally synthesized before. So we can also look at the particular chemical bonding in terms of this network plot in which the size of the nodes and the edges is proportional to the number of compounds we find. The main thing you can see here is that copper oxides really, really dominate. It seems to be the most prevalent way to achieve this screening. Maybe not so surprising given that those cuprates are copper oxides. We also see a good number of sulfides and selenides. And you do see that there is a good amount of chemical diversity in terms of the overall number of metals and anions that we do find. A nice kind of validation here is that several known classes of strongly correlated materials are kind of captured, are reproduced by this query. Okay, so one is these cuprates, such as La2CuO4. This is one of the classic parent compounds of the cuprates. We find that one. That would be a problem if we didn't, since we're looking for things similar to the cuprates. In addition, we also find other classes of correlated materials, such as these layered chalcogenides. And these systems are known to exhibit in some cases superconductivity and charge density waves and other interesting correlation phenomena. So a nice sanity check that our query is working here. So now we're down to 187 compounds, so okay, and that's a small enough number that I could actually go through and start to look at what some of these things are and further screen this down to find the best candidates. So the first thing I do is I get rid of any cuprates because those have been well studied. That's nothing new. And secondly, what I do is I consider the actual structure, the crystal structure here. So in a material that has an electronic structure like the cuprates, we want some electronic conduction pathway. Basically, we still need some finite hopping. We want U to be large compared to T, but we still need some conduction pathway. Therefore, we're going to ignore any candidate in which we don't have any connectivity between these transition metals. So for example, for this potassium iridate kind of compound, so this has these square planar iridium oxide units, they're not actually bonded or connected in any way. So therefore, this is unlikely to give anything reminiscent of a cuprate. Whereas for something like this thallium copper phosphate, you can see there is some connectivity network between these copper oxygen square planar units. So when we consider that, now we're down to just 26 compounds. So we're quickly starting to run out of compounds. You can see we still have several coordinations here, still plenty of square planar, some linear square pyramidal, as well as a few trigonal prismatic. So now we're down to just 26. It turns out even that is not sufficient to ensure that we'll get this single band correlated material properties. And there are a few things that can still go wrong at this stage. Basically, a few ways in which nature can still avoid this rare feature of a one-band model. And I'll describe those here. So the first thing that can happen is the material can just be too covalent. Basically, as exemplified by this nitride material, there can be too much interaction or hopping between the transition metal D states and the anion P states, such that we just get this delocalized, this broad metallic band. So we just have your usual itinerant metal. Okay, so another thing that can happen, such as in this cesium tungsten oxide case, so here you can see it looks like, okay, we got this narrow level, but you can see it's not half filled in this case. It's completely filled up. And what happens here is you can have too much bonding or interaction between the metals themselves. So in this case, the crystal structure is complicated enough that you have these multiple tungsten sites. Tungsten is a 5D element, and those d orbitals are less localized, so they start overlapping and interacting with each other such that you form a bonding and an anti-bonding level, your usual thing from chemistry. Then it just fills up the bonding level. So we just get what's called a band insulator. So nature kind of avoids what would have been a one-band model. And finally, in this last case, this thallium copper phosphate, it looks like we almost achieved a one-band model here. And what happens here is that you have distinct metal sites with different orientations. So you've just broken the symmetry between different sites, and you get multiple bands. In this case, you get two different bands instead of one, the one that you were looking for. So I am happy to say that we do achieve a few single-band correlated materials. So we were at 26 before, and then we end up with 5. So I'm showing you 4 here because 2 of them are essentially the same. If you switch out strontium or barium, this dispersion relation looks basically identical. You can see that in each of these cases, we have in red this isolated band that's half filled and half unoccupied. You can see that there's appreciable energy separation between the bands above and below. So I'll note a few things about these correlated one-band materials. So first of all of these contain copper. So it seems like copper is just the most prevalent way to achieve this kind of electronic structure. All except one are oxides, so everything except this copper dibromide. So again, as I showed before, these copper oxides really dominate. In addition, almost all of the cases correspond to square planar coordination, just as the cuprates also have a square planar coordination. The one that doesn't is this complicated pyrophosphate compound. There, the copper is square pyramidal. Maybe you could say, okay, that's kind of the closest thing to square planar. You just add one anion on top, essentially. We do find significant diversity in terms of the types of crystal structures we've achieved here. So first of all, we have these two have these kind of one-dimensional channels, whereas the pyrophosphate and the selenate compound has a more kind of layered electronic structure. And I want to point out also that ones like this copper pyrophosphate, this is a complicated structure and also a pretty complicated stoichiometry. So this is K3HCU2P4O14. That's something I never would have come up with. I never would have intuitively guessed that, like we thought about VS2. And it kind of highlights one of the nice things about this systematic, high-throughput approach to materials discovery, because our query, finds this just as easily as it finds just a simple binary compound like this copper bromide. In addition, I'll note that in addition to achieving this one band characteristic, we have evidence for these materials that they also will exhibit strong electronic correlations. So first of all, the single isolated band has a small electronic bandwidth, in all cases no more than 1 electron volt. So what that tells us is that effectively the U over T ratio is very substantial. We find that all of these compounds exhibit a magnetic instability, so that's another signature of the electronic correlations. And all of them except the bromide really are strong magnets, so they fully spin polarize even within the DFT, just the band theory level. So just like I showed you before for vanadium disulfide, already even within DFT, these compounds show strong signatures of electronic correlations. So to show you just the kind of scale of this search, I made this figure with all these different circles, which basically we start out with our haystack, basically all known material shown here in red. And as we progressively screen down, our circles get smaller and smaller. So you can see when we go to non-radioactive, then in terms of stability and chemistry, then it gets too small, so we zoom in. We keep screening by electron count and structure. You can almost not see a circle there. We zoom in further, and we get down, when we further down screen based on extended bonding. And finally, we've found our 4 or 5 needles in the haystack, these compounds. So with that, I'd like to conclude that in trigonal prismatic vanadium disulfide, we've engineered this single-band correlated material. And if synthesized, this could enable really unprecedented experiments on a strongly correlated material. We then took a more systematic approach based on a materials database screening with a query based on several factors and generated several additional candidates. And finally, I hope I've given you a flavor for how high-performance computing, quantum simulations, and in addition, this new area of materials informatics can enable us to design or discover materials, even with very particular, very specific electronic properties. I'd like to thank my funding as well as computational resources, and I'd be happy to answer any questions. Thanks.